Well, I think people are gradually joining the meeting. We were quite on time. We started sharp 1 o'clock. So hello, everyone. Thank you for joining the SN Applied Sciences webinar session today. I see some of the attendees are from China. I think from the time zone, it's around 8 p.m. Thank you for joining the webinar kind of out of office hours. Also from Spain, from Indonesia, India, welcome everyone. I am Amin Fatemi. I'm the managing editor of engineering at SN Applied Sciences Journal. And today I will host this session of the SNAS webinar series with Professor Elías Cueto from University of Zaragoza in Spain. We are very much delighted to have him here today. He is also one of our editorial board members that took the time to be present at this webinar. Today, he will talk about a very interesting topic of mechanistic models and machine learning, friends or foes. And we are very delighted to have him. A few words about the journal and the webinar series. The journal was launched in 2018, and we started the webinar series not long ago, about 6 months ago, so that we increase a little bit of exposure and collaboration between our authors, editorial board members, and guest editors. So if you're also interested, you have a topic, a research topic, a paper that you've published, and you want to talk about it, with the research community, you're more than welcome to reach out to us. You see, I hope this on the screen, our email address, that you can reach out to us and we can hopefully make arrangements. So one thing to note is please keep yourself muted. Also shut the video throughout the whole session. If you have questions, and I hope you do, please write them down in the chat box. And at the end, after Professor Cueto finishes his presentation, we will open it up for discussion. And I think we are all about the formalities out of the way. Professor Cueto, please take it over and start your presentation. Thank you.
Thank you, Amin. Thank you so much. Well, first of all, I will share my screen. I would like to begin by thanking the organizer of these seminars, you and all the people at the Springer Nature, for this opportunity to be here today with all of you. Is really a privilege. And well, I would like also to thank the co-authors of this work, the work I'm going to present today. My colleagues, Beatriz Moya, Kerkus Hernández, Alberto Badillas, David González, Iciar Alfaro, and Francisco Chinesta. And well, the topic of my talk, as you have just introduced, is about the need of combining mechanistic models and machine learning, and how to do it, and to open the discussion about the advantages and the disadvantages of each of the approaches. Because as many of you, if not all, known, science has changed a lot in the last years, and many people is talking about the fourth paradigm of science. If science began some 2 millennia ago as essentially something empirical, it changes to something theoretical with the help of mathematical language some centuries ago. And more recently, it became mainly computational. Computers came to rescue basically in the process of solving very complex equations arising from the theoretical point of view. Today, however, many scientific installations, facilities are producing tons of data, particularly big facilities like CERN in Switzerland or this type of facilities produce a huge amount of data every second. So by data exploration, scientists are being able to unify theory, experiments, and simulation. The increasing capacity of computers is making possible to store all this data in computers, and scientists are increasingly extracting knowledge by means of artificial intelligence, including new theoretical expressions for many observed phenomena. However, it is also well known that the biggest supercomputers in the world continue to be devoted to simulation. 8 up to the 10 most powerful supercomputers in the world continue to be devoted to simulation, thus demonstrating that simulation continues to be a challenging practice for us scientists, and that continues to have an enormous interest. So the key question here, particularly in recent times, is the need for speeding up simulations in order to obtain results. Very recently, NASA was asking coders to speed up their supercomputers because at the end of the day, both for academia and industry, speeding up simulation results is a crucial issue. So, well, we have an important capacity to obtain very powerful, accurate, high fidelity simulations, but the time that it takes to us continues to be a challenge. That's why very recently a growing interest has been detected on the so-called learned simulators. Learned simulators are simulation machines that are able to obtain predictions for physical phenomena of interest based not only in mechanistic laws, but mainly in data. We have all these experimental data that I mentioned before. So why not trying to extract simulations, predictions, to forecast the future based on this data? This is particularly interesting because this kind of learned simulators can be reduced for similar phenomena, but for slightly different problems in which we change slightly the value of the parameters for the simulation. And they are particularly interesting because the accuracy depends on data, crucially, not only on models, not just on the quality of the model. And they are particularly interesting for the so-called mini query framework. All these kind of problems in which we need to perform repetitive calls to simulators to obtain results. This is particularly interesting, for instance, for optimization problems. So there is a growing interest in this kind of simulators. However, the limitations of artificial intelligence, and particularly machine learning, are well known for all of us. And while AI has shown a tremendous success in many tasks, particularly for vision-related tasks, well, many people still complain about its black box behavior. It is particularly sensitive to noise in the data, for instance, and not always the results are interpretable, which is something that we as scientists and engineers, we would like to have an interpretability of the results. So it is important that we attract, I think it is the case, people from the field of applied mathematics to dive into the foundations of the mathematical foundations of artificial intelligence, so that we can reuse centuries of scientific knowledge and all this tradition in theoretical science could be incorporated in this new arising field. Well, another important limitation of artificial intelligence is that of cognitive biases. It is well known that artificial intelligence is very frequently blamed to have important biases, and particularly recently some problems with, for instance, racist predictions. Okay, for instance, in the US, some research has been done on the possibility of predicting, given a picture of your face, the probability that along your lifetime you will be jailed. Okay, so this type of predictions, artificial intelligence predictions, is simply nonsense, and usually produces biases results. However, while a cognitive bias is a systematic deviation from norm, there are other type of biases that are particularly interesting. And this is the case of inductive biases. Inductive biases are biases by which the artificial intelligence system can be trained to respond in situations that have not been seen before. Okay, so in order to construct inductive biases, all this tradition in theoretical science could be of much help to us. Why not employing all this tradition in theoretical science to just construct inductive bias to tell our artificial intelligence how to systematically go to the right solution to the query. So, well, for exploring the possibility of constructing scientific inductive biases, first of all, we are going to put the situation into a particular framework, which is that of dynamical systems. Machine learning, and particularly scientific machine learning, can be cast into the so-called dynamical systems equivalence, and this has been put particularly well by Professor Weinan E. some years ago. This problem can be cast, as I said, in the form of a dynamical problems in which a set of variables, Z, their evolution in time of Z, that's what the dot on top of the Z means, can be cast as a function, a nonlinear function, very often, that depends on time and on the state of the variables itself, given some initial conditions set of at time 0. In this way, supervised learning could be seen as the process of finding the flow map that takes your initial variables Z0 and takes them to their state at time capital T. Okay, so the problem of learning some physical law could be understood as to tune this nonlinear function f by regression. Employ your favorite technique to do this regression, but for instance, it's particularly interesting to employ neural networks. They are particularly efficient in this sense. Okay, but In this framework, thermodynamics has a role to play in this process. Imagine for a moment that we could go down to the molecular dynamics scale, where Newton equations apply, and assume that we were able to label every molecule of our problem and to track all the set of molecules a long time, so as to have an enormous amount of data and to learn from this data how the physical phenomena will evolve in time. Well, this is force. We are not in the position of labeling every molecule in our problem, but this scale is particularly useful. Why? Because at this scale, everything is reversible and energy is conserved. So if we are in the position of making Z, this set of variables, as the set of position and momenta of every molecule in the set, the evolution of this set is well known for all of us. This is given by the so-called Hamiltonian formalism of physics that tells us that the evolution in time of Z equals a matrix L, which is called the symplectic matrix, which is skew symmetric, and this matrix is multiplied by the gradient of energy, some expression that depends on the value of Z itself. Well, this is perfect. And a lot of works recently in 2019 and 2020, some 15 works have tried to impose this Hamiltonian formalism or its equivalent, the Lagrangian formalism, in order to impose conservation of energy to this learning procedure. In 2021, there are still a lot of more works in this framework. There is a growing interest in feeding the learning procedure with some known properties of the process, particularly energy conservation. However, we know that if we coarse grain the model, because we are not in the position of tracking every molecule in the system, if we coarse grain the model and go to a higher level of description, it is well known that we lose some details in the description. The effect of some unresolved variables of interest on future prediction is that there is no unique prediction for every state of this coarse grain model, and that ignore details influences the observed variables. And this is well known since the times of Gibbs and James. In other words, by eliminating some degrees of freedom of the system, we will produce some fluctuation for future predictions of the systems. And fluctuation is well known to be equivalent to dissipation by the fluctuation dissipation theorem. So this means that we will need to modify our formalism in order to introduce a new potential in the description of physics, which is entropy. This gives rise to the so-called matriplectic formulation of the problem, which is also known as a generic formulation. Generic is the acronym of general equation for the non-equilibrium reversible irreversible coupling, and basically is composed by two terms. First of all, the reversible one, just introduced, and then the irreversible one, which is composed by a matrix M times the gradient of entropy, this new potential, often called the massive potential. Okay, well, with this formalism, we keep track of the right thermodynamics of both reversible and irreversible phenomena. But for this to work well, we need to impose two additional conditions, the so-called degeneracy conditions. That means that, matrix L, the symplectic matrix, has nothing to do with dissipation. So L times the gradient of entropy must vanish. And conversely, matrix M has nothing to do with the conservation of energy. So by choosing L symmetric, as in the Hamiltonian formalism, and M symmetric positive semi-definite, we can easily demonstrate that this formalism ensures the conservation of energy in closed systems, as well as the second principle of thermodynamics. So in other words, to learn physics from data and at the same time ensuring the fulfillment of the laws of thermodynamics, we need to find from data the form of at least a numerical approximation of matrix L, a numerical approximation of matrix M, the gradient of energy and the gradient of entropy, subject to the degeneracy conditions. For this purpose, we have employed neural networks in which, first of all, we construct a first term for the loss function, in which we obviously are interested in the accuracy of the prediction. We add a second term to the loss to impose in a soft way the fulfillment of the degeneracy conditions, and finally a regularization term regarding the weights of the neural networks. And with this in mind, we construct neural networks able to predict the future states of our system. For instance, this is a test problem in which we have a tire that is facing a jump in its trajectory. So first of all, what we do is to train a sparse autoencoder. An autoencoder is a particular type of neural networks in which we unveil the intrinsic dimensionality of data. So with the help of numerical data coming from simulation, we first unveil the number of true degrees of freedom of the problem, even if this is a very complex finite element simulation. Well, not so complex, but nearly 7,000 nodes. Viscous hyperelastic model for the rubber. We train the autoencoder. We unveil the intrinsic dimensionality of the problem, and then we learn how the system evolves in time, okay, by means of what we call structure preserving neural networks, SPNNs. Well, we found that the actual number of variables, the latent variables governing the problems, is actually very low. The position of the nodes is governed by roughly 5 variables, the same for velocity and stresses. And we see how well our neural network captures the evolution of the system. Here we compare the reduced order model that this type of networks is able to perform with classical ways of constructing reduced order models, particularly POD, proper orthogonal decomposition techniques. Okay, you see here how the tire inflates and shrinks all the way along during the simulation. Well, if we keep track of the error in this simulation, we see that this kind of neural networks in which we impose the fulfillment of the two laws of thermodynamics behave very, very well. If we add some noise to the results, to the data, we see that the network is still robust with respect to the effect of this noise. If we, for instance, don't impose the fulfillment of the degeneracy conditions, results become worse, but it's still better that those that we could obtain by means of black box classical neural networks. So we see that it is important that we impose some physical structure to our neural networks. This can be also extended by adding some not just physical biases, but also geometric biases to the problem. And for this, it is particularly interesting the structure of graph neural networks. In general, geometric deep learning, the work of Professor Bernstein in particular, is interesting in the sense that it enables us to impose the structure of symmetric groups that are known to be present in the physical phenomena. So for us, a house is a house, even if we take a picture in which the house appears on the left of the frame, or in the right, the house becomes the same. Or even if we distort a little bit the house, it continues to be a house. The same can be said, for instance, for the Mona Lisa portrait. We can rotate the portrait, and we are in the position of easily recognizing that it is still the portrait of Mona Lisa. This same concept can be applied to physical phenomena, so that we can impose geometric properties to our simulations, particularly if data come from mesh-based simulation, finite elements, finite difference, finite volumes. So that graph neural networks are a particular type of networks in which we construct a graph composed by a triplet made of, first of all, V, capital V, are some learned functions related to the vertex of the graph that we identify with the nodes in the mesh. Epsilon are functions learned on the edges of the graph, which we identify with the connectivity of the finite element mesh. And finally, U is a set of parameters typical of the simulation. Think of the Young's modulus, Reynolds number, this type of coefficients. Well, we construct our graph neural networks, paying particular attention to the data located at the nodes, okay, the nodes of the simulation, and also for those data related to the simulation itself, gravity, Reynolds number, etc. Well, we compare our work with, first of all, the type of structure preserving neural networks that I've just shown to you, without no geometrical bias. We compare our work to that of DeepMind people, particularly the work of Prof and the collaborators. They employ no physical bias, no metriplectic bias, but they employ geometric bias. And finally, we combine both the metriplectic, the physical bias, the thermodynamic bias, and the geometric bias. And we compare the results. What we see, for instance, for a problem which is roughly a co-wet, a shear flow of a complex fluid, and already be viscoelastic fluid, this type of models, if you are not familiar with them, assumes some type of structure of the fluid at the microscopic scale. And we try to teach the system the behavior of the fluid for different Reynolds number and for different Weissenberg number. Weissenberg number measures the degree of elasticity in the fluid. And what we observe for the variables related to position, velocity, energy, and the conformation tensor is that always the combination of thermodynamic biases and geometric biases provides better results that the simulations provided by only graph neural network or only thermodynamic biases. The more physical information you add to your simulation, the better the results you will obtain. This is roughly the same for the field of solid mechanics. In this case, is a cantilevered beam, which is viscous hyperelastic, large deformations. Okay. Again, we see that the combination of both biases, the thermodynamic and the geometrical biases, gives always the better results for position, velocity, and stress tensor predictions in the system. So, with this idea in mind, with which we have tried to construct, is an artificial intelligence that could be able to understand physics, to interpret a physical scene, very much like babies learn physics, how the surrounding world works. Okay. We know that babies in between 8 months, 1 year and 2, usually play with everything around, just throwing objects, and just to learn how nature works, how physics works, and to obtain data from which construct a physical interpretation of their surrounding world. So we are in the position of constructing a similar system with the help of this type of tools. So the idea is to see simulation as an engine of physics understanding. With the help of a camera, we have here a glass with glycerin on the left and an empty glass on the right, in which we project the predictions of our system. You can see how the system is able to detect what is happening on the left and to, in real time, thanks to neural networks, to project the prediction for future events. You can notice how accurate the predictions are, just because we are not only learning from data. We learn from data, of course, but we also take into account all this scientific theoretical tradition of our grandfathers all around these last centuries. So at the end of the day, what we aim to construct is a sort of artificial intelligence able to equip a robot, for instance, to manipulate liquids. Okay. We feed the robot with simulations, SPH simulations for different fluids, water, glycerin, blood, butter, honey, mayonnaise, chocolate. And with all this amount of data, we construct reduced order models of these fluids so as to allow the robot to construct projections forecasting the future. Okay, here the glass is actually empty, but the robot is able to forecast what will happen eventually if some liquid will be in the glass. Here the difficulty is twofold. First of all, to train with the help of simulations, the artificial intelligence. But once this artificial intelligence is trained, we face an additional difficulty, which is that by means of a standard camera, we have limited access to experimental results. The only thing that we can see is the free surface of the fluid. We don't have access to anything related to the velocity field of the fluid, to the pressure field, stresses, or anything similar. So we face the necessity of extracting information from only some quantities of interest from the fluid. So we need to train a second process to our neural networks in order to be able to construct this type of simulators. Okay, this is the ground truth of the simulators, and with only a few snapshots of the fluid, we are able to construct a simulator that only takes into account the free surface. This is on the left what we see from the fluid, only a flat projection of the free surface of the fluid, and here the simulator of the results. So, well, in sum, the take-home message of our work in this field is, first of all, and very importantly, data is very important, but data is not enough. I'm quoting Karen Wilcox here. Karen Wilcox from the University of Texas, Austin, was giving a conference this same morning entitled "Data is not enough." And I agree completely with her. Data is not enough. We are in the position of ensuring the fulfillment of basic physical laws while learning physics from data. And it is very important that we impose all this existing knowledge about physics in the learning procedure, because the more data the more physics you add to the learning procedure, the less data you need, and particularly important, the more accurate the results you obtain will be. And particularly important, this type of methods are able to exploit geometric invariances present in the physical phenomena. For instance, all the invariances related to conservation of different magnitudes, particularly energy, but also geometrical invariances. So, well, just to finish, I would like to acknowledge the funding entities for this work, particularly the company ESIC Group and the Spanish Ministry of Science and Innovation that gave to us the funding to accomplish this work. And I will be happy to answer any question in the endings. Well, but just before thanking you, I mean, again, for this kind introduction. Thank you.
Thank you. Thank you. It was a wonderful presentation. I personally learned a lot. And I think the answer to the question, which was the title of this presentation, mechanistic models and the thermodynamic learnings and geometric learnings that we have, incorporating that into the learning phase of the machine learning, is indeed our friend, right? Not foe.
Absolutely. That's the take-home message. They are absolutely friends.
Okay, fantastic. So we have one question in the chat box. I don't know which slide they're particularly referring to, but I will just read it out. Does this neural network have some symplectic structure so that when you input states, the network can output the states in the dual space?
Well, this type of network not only has a symplectic structure for the conservative part of the phenomena, and therefore is able to output in the dual space if necessary, but it has a somehow more involved structure. It has a symplectic structure for the conservative part, but a metric structure in the dissipative part, thus given rise to what is often called a metriplectic structure. Okay, it conserves the right amount of variables, energy in closed system, and it dissipates the right amount of quantities, particularly entropy. So this is the right structure to ensure the fulfillment of the first and second principles of thermodynamics.
Okay, fantastic. May I go forward and ask another question as well? In geometric representations, or in better to say it, in physical phenomena that we have in nature, if you want to incorporate that, you're going to deal with a very expensive and extensive set of data that have to be updated based on milliseconds even maybe. Do we have enough of CPU speed and computer structure to incorporate that at the time that, as we speak, in our updating our models?
This is a very, very good question and very pertinent. Actually, what the type of techniques I have just introduced is able to do is to develop models at any level of detail for the description of physical phenomena. As I said in the introduction, the first option you always have is to go to the molecular dynamics scale, to the atomistic scale, because there the physical laws are simple, Newton laws. Everything is reversible in time, everything is conservative there. The physical laws are simple, but data is huge. Exactly. So you will never be able to describe the world going down to the atomistic scale, because the typical scale of data is the Avogadro number of molecules at least. This is simply huge. This is not feasible. But this is still the problem for many physical phenomena. And what our technique is able to achieve is a right description of the phenomena for coarse-grained models of reality. So if your computer is not able to capture, distill, curate, and handle all this huge amount of data, you are still in the position of developing models at a higher level of description. Of course, this model won't provide you with very detailed predictions about the physical behavior of your phenomena, but will still provide you with a correct description of it. And in some sense, this is what science is all about. A scientific model is, first of all, a parsimonious description of any phenomena. The ability of keeping only the relevant aspects of what you see in nature. Okay, keep the interesting things and discard all other phenomena that are disturbing you from taking a general overview of what is taking place. So we are confident in that all these kind of techniques could help to distill appropriate physical laws at virtually any level of description.
Fantastic. Professor Cueto, I would like to once again thank you for a very really enjoyable and informative presentation. On the screen, you see again our slide. Oh, we have another question. Let me just jump to it real quick. Sunbright asks, data is not enough. So how much data do you need to train a model like the water in the cup shown in your presentation?
Well, the amount of data is always the question in these cases, and how big your computer will be to handle of this data. In fact, data for this kind of liquid examples is not that big. These are standard abacus simulations. Probably many of you know the finite element software abacus that run in a typical Mac laptop. For these examples, we need absolutely no supercomputing facility. So they run in one of my students' laptop. The amount of data is not that big, provided that you incorporate into the process the right amount of physical knowledge. Okay, so again, the more physics you add to the problem, the less the less amount of data you will need to obtain accurate results.
Yes, indeed. Okay, thank you very much again for the presentation. You can reach the Professor Cueto through the email address provided on the screen if you had other questions, and the video of this session will be also available on YouTube in short order in a couple of weeks after editing. So thank you everyone, and thanks to Professor Cueto once again, and I hope to see you again in another webinar in the next quarter or so. And have a nice day, and bye-bye.
Thank you so much.
No problem.